All right, let's dive into something you probably see every day, but maybe don't think about: welding. We're going to explore the hidden science that literally holds our modern world together. It's pretty incredible. I mean, just look around. From the giant fuselage of an Airbus A340 soaring through the sky to the tiny, super strong gears inside your car's transmission, almost every complex machine we depend on is built on a foundation of welds.
But that kind of makes you wonder, right? How can we possibly trust these tiny seams of metal, often just millimeters wide, to handle insane amounts of force, day in and day out, without just failing? Okay, so to get the answer, we have to zoom way, way in. The secret isn't on the surface. It's deep inside the incredibly violent physics of a single tiny weld point.
And get this, we're not just talking about melting metal here. This quote reveals something absolutely extreme. The temperature at the surface often exceeds the boiling point of the material. Think about that for a second. The steel isn't just liquid, it's literally boiling.
So you can forget any image of a calm, glowing puddle. The weld pool is more like a tiny, chaotic ocean. It's this turbulent mess of violent fluid flow, metal instantly vaporizing, and just intense, rapid-fire pressure changes. And this isn't just some cool physics trivia. It has real-world consequences. That escaping vapor pushes back with a recoil force so powerful it can literally blast molten metal right out of the pool. That's what creates spatter. And it's a defect you really, really don't want in a quality weld. But, the real magic, or the real disaster, happens in the split second after the heat moves on, as that tiny ocean of metal cools. This is where the weld's atomic blueprint gets written, and it determines everything: its strength or its weakness.
This all comes down to a process called phase transformation. As the steel cools, its atoms literally rearrange themselves into new crystal structures. A good way to think about it is like water freezing into ice. But imagine if you could create different kinds of ice, some super strong and some super brittle. That's exactly what's happening here as the hot austenite steel transforms into various forms of cooler ferrite.
And this happens in one of two main ways. You've got a reconstructive transformation, which is kind of slow and messy. Think of a crowd of people slowly shuffling around to find new spots. But then you have a displacive transformation. This one is fast, coordinated, and dramatic, like a troop of soldiers snapping into a new formation all at once. It's a much more shear-driven change. Now, depending on the exact recipe of the steel and, crucially, how fast it cools, you get a whole menu of different final structures. You might get something like a siccular ferrite, which has these strong interlocking crystals that are tough and resilient. That's good stuff. Or, if it cools too fast, you might get martensite, which is super hard but also very brittle. It can crack under pressure. Getting the right one is absolutely everything. But here's where it gets even trickier. Even after the weld is cooled down and looks absolutely perfect on the outside, a hidden danger can be lurking inside. People in the field sometimes call it the ghost in the metal. We're talking about residual stress. I want you to imagine a powerful spring being compressed as tightly as possible and then trapped deep inside the solid steel. The weld can look totally flawless, but it's holding this enormous locked-in energy just waiting for a chance to release itself, usually by cracking. So, how does that spring get coiled up inside the metal in the first place? Well, the mechanism is called transformation plasticity. Remember that phase transformation we just talked about? As one part of the metal changes its atomic structure, it also tries to change its overall shape and size. So here's how it goes down. You start with a region of steel that's all one crystal structure. As it cools, it starts transforming into a new one, maybe martensite, which wants to take up a different amount of space. But the cool, solid metal all around it, it acts like a rigid cage, and it refuses to budge. So that strain, that urge to expand or contract, has nowhere to go. It gets locked in as massive internal stress. So let's just recap. The physics are unbelievably violent, the atomic structures are super complex, and the biggest dangers are completely invisible. How on earth can we possibly engineer welds safely and reliably? Well, this is where we zoom back out. Modern engineering has found an amazing way to tame all this complexity. We do it by designing welds with code, essentially creating a perfect digital twin of the weld before a single spark ever flies. And the power of doing it this way is just staggering. With these mathematical models, engineers can predict the exact final crystal structure. They can calculate those hidden stresses. They can figure out how to prevent cracking and distortion, all before they even touch the real piece of metal. Using this incredibly sophisticated software, they can run virtual experiments over and over again. They can simulate everything, from the chaotic flow in that boiling pool of metal all the way down to the final atomic arrangement in the cooled, solid weld. And this is what brings us right back to where we started. This predictive power is what makes it possible to engineer those critical aircraft skin panels and those high-performance automotive gears with a level of safety and precision that was basically unimaginable just a few decades ago. So really, the big takeaway here is pretty cool. By mastering this invisible, chaotic world of atoms and stresses, we build a safer, more reliable world that we can all actually see and touch. Which, of course, leaves us with one last thought. What other invisible sciences are out there right now, quietly shaping our future?